look at the structures, and since a few of you I very clearly saw spending a lot of time on one. Okay, we said there's three possible products. We're doing the substitution of a hydrogen for the acyl group at either the ortho position, the meta position, or the para position. When you looked at the intermediates generated, and this is the one case where I think we have all three. Okay, all three generate intermediates that have a carbocation. So all three are unstable structures by their sheer characteristics. And all three ended up generating three resonance structures. Right? But when we go through and look at those resonance structures, does any one of those resonance structures jump out and say, hey, this is really bad? Or maybe, is this really, really good? So when you look at the resonance structures for structure 1, do we have any resonance structures that you're like, that's a good option, I like that one? And if so, what is it? Okay, if we look at the boards up here, we've got the ortho. Which one are you saying is really, really good?
The tertiary.
Right. End up noticing that in our tertiary system, in our ortho substitution, we end up with a tertiary carbocation. Why might that be important to reference? It's more stable. So if I'm looking at the mechanisms up on the board, ortho versus meta, the ortho generates more stable intermediates. What does that mean about the activation barrier to generate the ortho product? It's lower, which means it's going to form faster. So ortho should form faster than our meta. What about our para substitution, which is our blue board on the left?
It also has a tertiary.
We also have a tertiary carbocation showing up within it. We now have kind of an interesting dilemma here because both of those generate the same kind of stable carbocation. Where is that one? Right here in the middle. Okay. So, interesting. If our ortho and our para both generate lower energy intermediates, we would expect those products to form first. Okay? So we could now start to perhaps reference that if we saw a methyl group, we would predict our substitution to occur at our ortho or para positions. Okay? What happens when we move to structure 2? So that's our purely backboard. Our structure 2 drawers went through and gave us the ortho and the meta results. Right, do we notice anything interesting in that set? Okay, again, we're looking at our carbocations, our intermediates. Is any one of those more or less stable than any of the others? The ortho in that last structure gives us something that I've referenced as tertiary, though technically our definition isn't really tertiary. So we can call it secondary, and then what you might be referencing. Carbocation will always be allylic. It's not a good idea to reference it as allylic here. It's more appropriately referred to as the arenine cation. There's something very special about that last one. And remember, we can't really call it tertiary.
You can have resonance from outside the ring.
It is secondary plus resonance. Okay. If we looked at our reactivity of our carbocations, resonance always made those go faster in SN1 conditions. They overly stabilize our carbocations. So when we look at our ortho position, okay, we've got our tertiary or secondary plus resonance, okay, which makes a very, very stable carbocation. The meta position really didn't give us anything. Any guesses as to what we'll see in the para? We'll see the same result. We'll get a tertiary or our secondary resonance, depending on how you want to look at it, for our carbocation. Okay, so now not only if we have methyl groups, but if we have a nitrogen, Okay, and amine. Oops. Ooh, I'm about to draw on the iPad. Let's try that again. Okay, if we have an amine, that starts to favor these ortho and para positions. Right? I unfortunately drew this all really, really big, so I'm going to have to clear everything away and try again. What happens if we looked at structure 3? What results did we get?
You have a tertiary, well, secondary. No.
Structure 3, we got two answers. There's one on the board, on the front board, and there's one on the back board in green. And the back board's been switched to our meta. The front board is para. What patterns do you notice? Do you notice anything jumping out as being like, oh my god, that's really stable, like we saw with 1 and 2?
Meta has just secondary, and then the para has secondary sort of.
Okay, so we ending up with the same secondary all the way through. And I'm hearing with the para that we have a secondary plus resonance. So in that secondary plus resonance, which one are you referring to here? Left, middle, right?
Middle.
We're going to middle. Okay, I'm going to make one quick adjustment because you guys did miss one thing here. Notice the positive charge. So I do agree you should absolutely be looking at that middle one. Is it plus resonance?
Well, I was thinking it would make, it's not a really great resonance, but it is resonance. You can
How?
make the oxygen positive, moving the double bond from the oxygen to...
No, you can't do that. Oxygen is more electronegative than the nitrogen. You cannot pull electrons from that oxygen. Those electrons will go to the oxygen and to the oxygen alone. If you want to do resonance from the negative oxygen across, that's fine. But then the nitrogen has too many bonds. What happens? Okay. You have a positive next to a positive. Is that structure good? No, that is incredibly bad. So in our para substitution in this case, we've not found a super stable carbocation. We actually found an incredibly unstable carbocation. And we notice that with our para position. Okay. Very bad resonance. What is that going to do to the stability of the para intermediate? Make it unstable, which does what to its energy? Increases it, which means what is the likelihood of forming the para substitution product for 3? Very, very unlikely. When we look at the meta product, do we end up forming any particularly stable carbocations? No. Do we form any particularly unstable carbocations? No. So the meta product isn't particularly good, but it's not particularly bad. If you go through and draw the ortho intermediate resonant structures, what are you going to end up finding? You're going to find the same things that we saw for the para. You're going to end up with very bad resonance. Okay. This is an interesting result that's starting to come out of this.
Plus, when you have the electron density at the, like, just because the oxygens are so negative.
I haven't looked at 4, so I don't know. Oh, you're saying electron density in 3?
Yeah.
So what you're starting to reference is the electronegativity of the oxygens on the nitro group are withdrawing electrons. All of those electrons are getting withdrawn ultimately then from the nitrogen. Now the nitrogen's very positive, so what does it start to do? Pull electrons from the ring. What did our ring have to act as in our EAS mechanism? A nucleophile, an electron donor. our starting structure has no electron density in the ring because our substituent is drawing electrons out of it. Well, if there's no electrons in the ring, can it act as a nucleophile? No. Okay. So what you've just alluded to there, Cassie, is that I wouldn't really expect to get much of a reaction here at all. Okay. Do we have enough yet to start making comparisons? What is different about the atom in 3 than the atoms in 1 and 2? What do you mean electron donating versus electron withdrawing?
So we get enough donating electron density towards the ring versus the nitrogen, which is pulling electron density away.
Okay, so you're saying the nitrogen, by nature of its electronegativity, is withdrawing electron density, so we get a different result when we compare 1 versus 3. Fair enough. What's the atom in 2? It's a nitrogen. So you have an interesting theory, but it's falling apart already because I have an electronegative atom attached to the ring in 2. And in 2, what did I end up getting? I got the orthopara actually working. I actually had legitimate good results in those. So it's not an electronegativity effect here. Okay. Look at the atom attached to the ring in 3. It carries a positive charge. It's not that it's electronegative per se. It's that it doesn't have any electrons. If we go through and look at the atoms in 1 and 2, 2 for sure has electrons. There's a lone pair there. 1 didn't have any electrons. Why would it direct as our ortho and para? It's a bit odd. It doesn't actually have electrons, and yet somehow or another we're still seeing this favoring for that ortho and para position. Okay. What happens when we shift to 4? What would we expect 4 to result for us? Should it match the results of 1 and 2 or the results of 3? Okay, why would it match the results of 3 and not 1 and 2? I mean, if I look at that, the atom next to it is carbon. That should match 1. Why is it partially positive? There's a resonance contributor that puts a formal positive charge on our carbon and a negative charge outside the ring. The atom immediately attached to the ring has drawn electron density away from the ring. We're now starting to look more like structure 3 than we are 1 and 2. If we go through and look at the resonant structures, which I already forgot, 4. What do we have 4? We've got on the front right board or front left board the para product, and on the back board we've got the meta product. Same deal. Look for patterns that you see within those. What do you notice? Does any resonant structure jump out as like, ooh, that's a bad idea? Okay. Which structure? Top, middle, bottom? What's the issue with the middle one? What do you mean 2 positives-ish? I see a tertiary carbocation. It's got 3 carbons attached to it. Why is that bad? Draw that extra resonance contributor. What's the result? That para-substitution product generates an incredibly bad resonance structure. What are we going to notice if we look at the the ortho position? Same deal. We'll end up with a very bad resonance. When we look at the meta, do we see anything particularly good? No. Do we see anything bad? No. Okay. So when we look at the results of 3 and 4, both of those end up generating a very poor reaction. Okay. 1 and 2 end up being actually faster reactions. These end up being really, really good reactions. Why would they be good in comparison to 3 and 4? What did they do to the intermediate? It made the reaction more energy or energetically favorable with 1 and 2. Okay, so again, we want to try and come up with some way to pattern these. If we look at 1 and 2, the atom attached to the ring has some electron density. If we look at 3 and 4, the atom attached to the ring is missing electron density. We're looking at a positive charge immediately next to the ring. If we put a positive charge next to an electron-rich benzene, where do the electrons go? To that positive charge. They can no longer act as a nucleophile and leave the structure. This works for all aromatic structures. What you end up evaluating is looking for patterns. The pattern that we're trying to find is identifying the atom attached to the ring. Nothing else. Keep your focus at that atom and see what happens. If that atom has more electrons, it ends up generating our ortho and para favoring, like we saw for 1 and 2. If that atom is positively charged, so has less electrons, then we end up seeing a disfavoring for the ortho and para. Well, if we disfavor ortho and para, what does that mean? What's left? Meta is left over. So the analysis that I had you guys go through on the boards was looking at the intermediates. That is the official way to be looking at any reaction and deciding, is this a valid one? You look at the actual products, the steps. You don't know what to do, you guess. You draw it out, you look at it and say, oh, that was a horrible thing to do, I'm going to undo that, and I'm going to try again. The other way to approach it is by looking at your structures and looking for some sort of reactivity. In the case of the X having more electrons, those electrons can be donated via resonance downwards, putting negative charge at the ortho position. Is there resonance to further stabilize that negative? Yeah. Putting the negative charge at the para position. I now have negative charge at the ortho and para positions. In the EAS mechanism, my aromatic ring acts as a nucleophile, an electron donor. Well, which positions on the ring are going to be more active as a nucleophile? The ones that are more negative. And I'm definitely running out of time, and I apologize for those of you that have to leave, so give me a real quick second. Draw out the next one. If we have a positive charge atom, we end up drawing electron density moving out of the ring in our resonance contributor. What charge builds on the meta position? Trick question. No charge builds on the meta position. What charge builds at the ortho and para position? A positive charge. Okay. What's going to happen to the reactivity in an EAS reaction now? The ring is positive, can it act as a nucleophile? No. So if we have this case where X is less or has a positive charge, it's not going to be very likely to move forward in an EAS reaction. It doesn't have the electron density to do the reaction. If atom X has more electrons, we now put negative charge at the ortho and para positions. It is more active and more likely to react. Okay? So we can speed the reaction in that case. We will pick up there because I